Hello everyone, I'm going to introduce our work OceanSplat, Object-Aware Gaussian Splatting with Trinocular View Consistency for Underwater Scene Reconstruction. Our goal is to reconstruct a 3D scene from an underwater image stream. Most modern 3D reconstruction methods start by estimating camera poses and initial point cloud using SFM, and then apply neural rendering methods such as NURF or 3D Gaussian splatting. Underwater scene reconstruction generally follows the same pipeline. To improve underwater reconstruction, recent methods integrate underwater image formation models into neural rendering pipelines using MLPs to model attenuation and depth-aware backscatter effect. This enables physically rounded rendering and leads to better underwater reconstruction results than using in-air-oriented methods such as 3DGS. However, as you can see here, geometric consistency is still a major challenge. In particular, for underwater scene reconstruction using 3D Gaussian splatting, it is difficult to achieve strong performance without explicitly enforcing geometric consistency across multiple views. Fundamentally, underwater images suffer from limited visual information due to attenuation, backscattering, and low illumination, which make it difficult to represent distant objects. In addition, if geometric consistency is not considered, some distant 3D primitive may fail to represent the real object and instead capture the water itself in the training views. As a result, these primitives can appear as artifacts in novel views. Motivated by this observation, we introduced Trinocular view consistency to improve geometric alignment across multi-views. Starting from a monocular camera pose, we render two additional views by translating the camera horizontally and vertically. We then enforce consistency among the three rendered views. In 3D Gaussian splatting, 3D Gaussians are projected into 2D screen space and optimized using a pixel-wise photometric loss. By applying these laws across the trinocular views, we encourage Gaussians representing the same object in scattering media to not vary too much across different camera rays. And using a orthogonal baseline along the x and y provides non-redundant geometric constraint, which significantly improves multi-view geometric consistency in 2D screen space. By incorporating this trinocular view consistency, we propose OceanSplat, an effective framework for underwater scene reconstruction. First of all, we use MLP for rendering the medium and 3D Gaussian for rendering the object following recent underwater 3D reconstruction method. In this process, to enforce the proposed trinocular view consistency, we rasterize the scene from the camera poses translated along the horizontal and vertical directions, generating multiple rendered views for consistency enforcement. At this point, we use different baselines to account for sensitivity to both far and near regions. Next, we compute disparity from the rendered images and depth maps, and use it to rectify the rendered images back to the original camera pose via grid sample inverse shifting. We then enforce pixel-wise consistency between the rectified images. For view consistency, we first align the rendered result before applying the medium. After incorporating the medium effect, we then enforce consistency with the ground truth. Additionally, we reuse these synthetic camera poses for epipolar depth prior, which is designed for self-supervised depth regularization. First, we get the projected Gaussian 2D positions with high opacity as key point for epipolar geometry. We then apply triangulation between these key points to compute the depth in the original camera. And then we reduce the gap between the depth from epipolar geometry and the depth from alpha blending. So this allows depth regularization as a self-supervised manner. And we also leverage depth residual loss, which reduces the difference between the alpha blended depth and z values of each Gaussian along the ray for reducing floating artifacts. In addition, we introduce depth-aware alpha adjustment to suppress the formation of 3D Gaussians in water-occupied regions during the early stages of training. Early in training, 3D Gaussians often overfit to water regions, learning water intensity and causing floating artifacts in novel views. We empirically observe that applying view-dependent opacity from MLP during early training prunes these suboptimal 3D Gaussians and reduces such artifacts. Through this approach, we are able to effectively reconstruct underwater 3D scenes. The learning objective consists of the standard photometric loads used in 3D Gaussian splatting, combined with our proposed trinocular view consistency loads, epipolar depth regularization loads, and depth residual loads. Each consistency loss is implemented using a regularized L1 formulation. Specifically, the OGJ stereo loss involves view consistency before applying medium, while the full stereo loss involves consistency after the medium is incorporated. And we additionally employ a disparity smoothness term to mitigate disparity noise during inverse shifting. Furthermore, we align the epipolar depth prior with the rendered depth using an edge-aware log L1 load. Finally, a depth residual load is applied between the z values of each 3D Gaussians and the upper-blended rendered depth. We conduct experiments using both real-world underwater dataset and simulated dataset. For real-world dataset, we use the see-through NERF dataset, which contains 4 Cs, as well as 2 selected scenes from the in-the-wild dataset. For the simulated dataset, we use the NERF LLFF dataset and apply depth-aware attenuation to generate underwater and foggy scenes, respectively. Training iterations are set adaptively based on the number of frames in each sequence. Rendering quality is evaluated using FSNR, theme, and RPF metrics. Experimental results demonstrate that our methods achieve superior performance over previous underwater 3D reconstruction approaches, not only in terms of RGB rendering quality, but also in depth geometry consistency. This improvement is largely attributed to the significant reduction of floating artifacts in novel views enabled by our proposed approach. Furthermore, our method attains state-of-the-art results on both scenes in see-through NERF and the in-the-wild dataset across all evaluation metrics, including PSNR, theme, and RPFs. Our method also demonstrates strong performance on simulated underwater and foggy scene dataset. For the simulated dataset, we evaluate both scene reconstruction and scene restoration, where attenuation effects are removed to assess alignment with the original in-error scenes. Experimental results show that our method achieves the best performance in scene reconstruction, that is, novel view synthesis, under both simulation settings. Furthermore, in the scene restoration task, where attenuation and medium color are removed after reconstruction, our approach also delivers strong performance. Qualitative results show that existing methods entangle floating artifacts with the scattering medium, causing black hole during attenuation removal. Our approach improves medium object disentanglement, allowing robust restoration that removes only the scattering medium while preserving scene object. We further validate the effectiveness of our methods through extensive ablation studies. Compared to prior approaches, our method achieves superior performance without incurring significant overhead in training time, rendering FPS, and VRAM usage. The ablation results on effectiveness demonstrate the individual contributions of each proposed component. Finally, through experiments with various television configurations, we show that the proposed triangular view consistency with orthogonal baselines consistently outperform other configurations. This result highlights the effectiveness of our proposed non-redundant positional regularization. As shown in this real-time rendering video, our approach significantly reduces floating artifacts and yields more geometrically consistent results compared to the baseline method. To wrap up, I'd like to summarize the key takeaways of our work. First, we introduced a novel method using trinocular view consistency to maintain stable scene geometry even in difficult scattering media. Second, by leveraging translated views, we derive epipolar depth priors, which serve as an effective self-supervised regularizer for depth. Third, our depth-aware alpha adjustment successfully mitigates floating artifacts by regulating 3D Gaussian opacity during the early stages of training. As a result, OceanSplat achieves superior performance across both real-world and simulated scattering datasets. Thank you for listening to our presentation.